Okay, at this point, I'd like to go out of order in the section number. So we just covered section 12.5, and at the end of section 12.4, and at the end of section 12.4, we talked about one measure of the goodness of fit, of overall fit of a regression model, and that's the R squared. Okay, another measure of overall fit can be found doing an analysis of variance. Okay, and this analysis of variance is going to lead to an F statistic, just like we looked at from chapter 11. Okay, so the F test for overall fit, the statistic is calculated in 3 equivalent ways. So in the middle here, you can see that we've taken the ratio of the explained sum of squares divided by the unexplained sum of squares divided pretty much by the sample size, n minus 2, the degrees of freedom. So this denominator is called the MSE, the mean squared error. Okay, and that's interpreted as the average of the squared error terms. Okay, and similarly, we divide SSR by 1 because we have one regressor in the model, and we call that the mean squared regression, MSR. Okay, so the F statistic is the ratio. Intuitively, you'd think of the F statistic as a ratio of the explained variation to the unexplained variation. So as this ratio increases, as it gets larger, that is telling us that the model has a better fit. Okay, and this F statistic, computed up here, F statistic, okay, should be compared to a critical F value that you can find in Appendix F to determine statistical significance of the model. So the R squared statistic does not have a critical value. It's just a scalar that goes from 0 to 1. The F statistic can actually tell us if the model is statistically significant. So when we calculate a regression model using the data analysis tool in Microsoft Excel, the output will produce an analysis of variance table. And that table will include the source of the variation. So SSR is in the top, the explained variation is in the top column, top row. The unexplained variation is in the middle row, and then the total variation is in the bottom row. So here we have the SSR formulas, the unexplained sum of squares formulas, and the total sum of squares formulas, and their respective degrees of freedom in the third column. The fourth column, calculate those mean squares for the regression and for the errors. Okay, and these are the same, these are the values that we just saw in the F table. And then the F statistic is called F calc in the textbook, and that's MSR divided by MSE. Okay, and Excel is going to produce for us not the critical value for F. Okay, we still have to look that up, or we can find it using an Excel formula, but we're probably just going to stick with the p-value that Excel is going to produce for us. And if you typed in this Excel expression formula equals fdist with the F calc, the F statistic from this portion of the table, and then 1 for the degrees of freedom of the numerator, and n minus 2 as the degrees of freedom for the denominator, then you'll get the p-value. for this f-test. Okay, now we can get back to section 12.5. This section is where we learn how to calculate standard errors for our parameter estimates. Okay, and that calculation begins with what's called the standard error of the regression. And the notation for the standard error of the regression is lowercase s sub lowercase e. Okay, so the standard error of the regression is equal to the sum of squares for the error terms, which is our measure of the unexplained variation, divided by the degrees of freedom for the model, or for the error sum of squares, and the square root of that. So it's the square root of the mean squared error. Okay, that's what we call the standard error of the regression. So the smaller the standard error of the regression, the better the fit of the model. But the standard error of the regression is a number that's similar to the covariance. It's difficult to interpret by itself because it depends on the units of measurement of the dependent variable. So there's no good rule of thumb about what's a good standard error of the regression or a bad one. But it is a useful input into a number of other ways of evaluating a regression model. Okay, and in this section of the book, it is what we use to begin to estimate the standard error of the individual parameter estimates. And we'll use that to construct confidence intervals for our parameters and t-statistics that we can compare to critical t-values to see if our slope and intercept parameters are statistically different from zero. Okay, so the standard error of the slope, okay, can be calculated in a number of ways, and that's what all of this mess is. The good news at this point is that we'll never calculate these standard errors of the slope and intercepts by hand. It's all being done by the computer for us. It's possible to do this. We've already computed the sum of the squares errors in a spreadsheet, and we can compute the standard error of the regression model fairly easily at this point. Okay, and I might show you how that's done in a little bit, but we'll never have to worry about that again. So the standard error of the slope, so s, lowercase s sub b1, is equal to the standard error of the model, and then that is normalized by the sum of the squared deviations of the dependent variable from its mean. Sorry, the independent variable from its mean. And then the second equality sign, I'm just reminding you what the standard error of the regression is. That's the square root of the mean squared error. And then that's divided by the sum of the squared errors for x. Okay, and the ratio of two square roots is the square root of the ratio. And so one way you can think about these standard error of the slope is that it is equal to the square root of the variance of the slope. Okay, so this is measure the variance of the slope. Okay, and like all standard errors, the standard error of the slope is going to decrease with increases in the sample size. And then the standard error of the intercept, okay, S sub BE is equal to the standard error of the regression multiplied by this ugly thing underneath the radical sign. So 1 over the sample size plus the mean of the independent variable squared, and then divided by the sum of the squared deviations from the mean for the independent variable. Again, there's not much intuition to this statistic. Okay, but with those standard errors, we can conduct hypothesis tests. And I'm just going to present the two-tailed hypothesis test because that is what is presented by most statistical software packages. But if we want to conduct one-tailed hypothesis test for a slope or an intercept, we can easily do that using the logic that we've used in the past. Okay, so for the slope, we're testing whether the beta 1 is equal to 0, and then the alternative hypothesis is that whether the beta 1, the theoretical slope, is not equal to 0. So the t-statistic is equal to, and here we're testing to see if it's different from 0, is equal to the slope itself divided by its standard error. Okay, this is just like a means test, where 0 is the benchmark mean. Okay, and this is the t-statistic that Excel is going to produce for us automatically. Okay, we can construct another t-test if there's another benchmark that we want to test the slope against. So suppose you want to test if the slope is different from 1, then you would just subtract 1 from the slope and divide that by the standard error. And you would have a different t-statistic for that particular test. And then for the intercept, the null hypothesis is if beta 0 is equal to 0, and the alternative is if beta 0 is not equal to 0. And then the t-statistic is constructed in a similar way. Okay, and then confidence intervals can be constructed just like we've constructed confidence intervals before. So the lower and upper limits of a confidence interval is equal to the coefficient, the slope estimate. Okay, the lower interval is the slope estimate minus the t-value for any particular alpha level, so maybe 1.96 if our alpha is at 0.05, then multiplied by the standard error. And then the upper limit of the confidence interval is the slope plus t times the standard error. And then the intercept, the confidence interval for the intercept is constructed in the same way.